5.
Anybody have an objection to going to 5? All right. There was an objection? Okay. For the life of me, I have the hardest time with, this is going to be hilarious, binary things. Things that are like one or the other, like remembering which is which.
As far as nearly or more in this case?
Yep. Output values, okay, meal, okay, all right, got it.
About the only thing that
Usually I can ask and it ends up being correct, and but I would hate to ask and have the person tell me the wrong thing and have it wrong. Okay, so the first thing that we need to do is make sure that we know the difference between mealy and more. And I just looked it up, and okay, mealy depends on the input and the current state.
and more on it gives you the value after, or the output after. Let's see.
The output depends on state only. This will make more sense after we've done it. I just wanted to write it down so I had it so that I won't forget it later. So a mealy machine, the output depends on both the input and the current state. You have to know the state of the machine and the current input in order to know the output. For more, you only need to know what state it's in. Okay, so for example, if I can't come up with a good example. Let's see.
Well, whenever, like on the exam here, it says like, gives you the output of 1 on the next clock cycle, means that it's equal.
Yes. Yeah. I was trying to think of like a real world example. That I'm just drawing a blank. Okay. All right. So there are a couple things that you can look at that give you some hints for mealy and more. So mealy and more, when you're doing a sequence detector like we have here, mealy, you can get the output on the current clock cycle. And so if the problem says on the current clock cycle, it's going to be mealy. If it says the next clock cycle, it's going to be more. More has one more state than mealy. And it's easier to draw the state table and to get the circuits for it. Okay, so we want to give the state diagram for a circuit that detects the sequence 0, 1, 0 and gives an output of 1 on the next clock cycle after the sequence is detected. Otherwise, the output is 0, overlaps are allowed. So we're looking for 0, 1, 0. What this means is you have these numbers that are being given to you, and when you get a sequence of a 1, 0, 1, then on the next clock cycle, your output is going to be a 1. If you didn't get a sequence of 1, 0, 1 on the last inputs, your output would be 0. So, like if I have my first input is a 1, and then a 0, and then a 0, and then a 1, and then a 0, and then a 1, and then a 0, and then a 1, and then a 1. Let's say these are my inputs. Then my output here is 0. There's no way I could have had a 1, 0, 1 on my last three inputs if I didn't have three last inputs. My output here is 0, and my output here is 0. Now here I want to look where my last three 1, 0, 1. And the answer is no. Okay, here were my last three 1, 0, 1. No. Here were my last three 1, 0, 1. No. Nope. Here were my last three 1, 0, 1. Yes. Here were my last three 1, 0, 1. No. How about here? Yes. And then whatever my next one was, it would be no on that one. Okay? So that's how it works. So you want to think about what your steps are towards getting to that golden output of, hey, I detected my sequence. So if you get an input of 1, that's your first step. That's getting you somewhere. If after you get a 1, you get a 0, that is getting you further. If after you get a 1, you get a 0, and then you get a 1, that is the state where you say, yes, I've met my sequence. What if I start and I just have a 0? Is that making any progress at all? No. So I'm going to have that be my reset state. My reset is I'm putting this in parentheses. That's not an output or anything, that's just what I've gotten. So reset, and I can also just put reset here. The same as if I've gotten a 0. Now, if I have a 0 and I get another 0, have I made any progress towards getting my sequence? No. So I write that like this. I'm going to go back to the same state that I was in. And I need to, for each state, I need to look at what happens if I get a 0 or if I get a 1. If I get a 1, have I made any progress? Yes, I've made progress, and I'm now at the state where I'm just putting this in parentheses. This is not an output or an input. It's saying I've got a 1. I'm at this state right here. So I can call this state A. I'll call this state B. Now I need to figure out what happens if I get a 0 or a 1 if I'm in state A. If I get a 0, state B. If I get a 0 and I'm in state B, so I'm in state B, that means I'm right here. I have a 1. If I get a 0, have I made any more progress towards my sequence? Yes. So 0. And I'll call this state C with this little 1, 0 in here. All right, what if I get a 1? So I had a 1, now I got a 1. Have I made any progress? Have I lost progress? I'm still in the same state. I still have that 1. So I want to see, these are my stages towards getting the output. I still have a 1. My last input is a 1, so I'm there. Okay, so now I'm in state C. State C means I've gotten a 0, 1. If I get a 0, I now have 1, 0, 0. Have I made any progress? Have I lost progress? I've lost all of my progress. Yeah, I don't have anything anymore. I have to go back to here. Because now I don't have my last, so these are my states. My last digit is a 0, my last digit is a 1, my last 2 digits are 1, 0, or my last 3 digits are 1, 0, 1. So if I get a 1, then that's going to bring me to state D, 1, 0, 1, state D. And I still need to figure out what happens if I'm in state D. So if I'm in state D, I've got a 1, 0, 1. If I get a 0, am I in any of these states here? Well, let's
Yes,
look.
you go to state C.
I'm in state C because my last two digits are 1, 0. So I want to figure out what my states are ahead of time. So I could go back to A, but that's not, I can do better because my last two digits are now 1, 0. So if I get a 0, then I go to state C. Okay, now if I'm in state 1, 0, 1 and I get a 1, what state am I in now?
B.
I'm in state B. So I'm seeing there's a lot of confusion here. Let's just look at this. So we determined that these were the steps towards getting to our progress. And we have call these A, B, C, and D. So let's look at state D. I have 1, 0, 1 currently. My two possibilities of having after 1, 0, 1 is having 1, 0, 1, 0 or 1, 0, 1, 1. I need to figure out which of these four states I'm in. Start with D. Are my last three digits 1, 0, 1? Not for either of them, so I'm not in state D. Are my last two digits 1, 0? Yes. So if I got a 0, I'm going to state C. Is my last digit, so this one is taken care of, is my last digit a 1? Yes. That brings me to state B. If I don't have any of those things, then I'll be in state A. Okay, now this is a Moore machine, which means that our output depends only on the state that we're in. And so our output depends on whether we got a 1, 0, 1 on our last clock cycle. The only one where that was true was this one. And for a Moore machine, you can just write the output on the state itself. So here's our state diagram. Let's do the state table now. We have our four states, A, B, C, D. Our input,
Just to clarify, I'm sorry. We're doing the sequence 1, 0, 1, right? Instead of the 0, 1, 0
yes, I did the wrong sequence. Thank you, yes, I did. I did the problem, I did a different problem. I did a sequence of 1, 0, 1. 1, 0, 1. So I can real quick, let's do 0, 1, 0. Let's see how that goes. So our states would be 0, and then 0, 1, and then 0, 1, 0, and then a reset or a 1. So that'd be A, B, C, D. I'll give you 2 minutes to see if you can draw the state diagram, and I'll do it myself over here.
would technically be
One or reset, yeah. And there it is up there. So I don't think it's been 2 minutes yet, but I'll explain it in just a few seconds. And by the way, you can be more, you can have like more detail on these if you want to. I could write, if my input was V, I could write V equals 0 on each of these. And if I wanted to write, my output, whatever it is, I could write that. Okay, so if we're trying to detect 0, 1, 0, as the problem said, if our first bit that we get is a 1, that doesn't do us any good at all. That's nothing. So we can also make that the same as our reset state. So that's if we get a 1. But if our first bit is a 0, then we've got our first bit on our way to our sequence. And so that would be, if I'm starting from my reset and I get a 0, then that brings me to state B. Now from state B, if I get a 1, that brings me to my next state. But if I'm in state B, that means I've gotten a 0. If I get another 0, it is still true that my last bit that I received was a 0, so I stay in state B. If I'm in state C, that means I have a 0, 1. If I have a 0, 1 and then I get a 1, that puts me all the way back at state A, because my last bit is a 1, which is state A. But if I'm in state C, which means I have a 0, 1 and I get a 0, that means I've gotten the sequence I want. That brings me to state D. If I'm in state D and I get a 0, that means I have 0, 1, 0, 0, which matches up with state B. So if I get a 0, I go to state B. If I had 0, 1, 0 and I get a 1, that matches up with state C. And so I would go to C. The only time my output is 1 is for state D. So now let's do the correct state table for this. So you can call your states whatever you want. A, B, C, D. I didn't tell you what the name of the input was. I'm going to call it V, input V. And I'll have V equals 0 or V equals 1. And we'll say what the next state is. A Moore machine will just have one column for the output. It doesn't depend on the input. If this was a Mealy machine, the output would have to have different columns for the two different inputs. So when I was in state A, if I got a 1, I stayed in A. If I got a 0, I went to B. When I was in B, if I got a 0, I stayed in B. If I got a 1, I went to C. When I was in C, if I got a 0, I went to D. And if I got a 1, I went back to A. And when I was in D, if I got a 0, I went to B. And if I got a 1, I went to C. And my output was 0, 0, 0, 1. And then it says, produce the state assigned table. Use one hot encoding to represent the states. Okay, so one hot encoding means it's not using the minimum number of flip-flops. The number of bits you use for your states depends on the number of states you have. How many states do we have? We have 4, A through D. So if I only have 2 states, I need 1 flip-flop. If I have up to 4, I have to have 2. If I have up to 8, I can have 3. If I have up to 16, I can have 4. I can always have more than that. But, so if I had 10 states, I would have to have 4 flip-flops. But this one's different because it says use one hot encoding. What that means is I need to have just 1 bit being 1 like a decoder or for each state. So I have to use 4 bits if I have 4 states for one hot encoding. For one hot encoding, you have to have as many flip-flops as you have states. And I'm labeling them 0 through 3. And this was saying that I'm making A is equal to 0, 0, 0, 1, B is 0, 0, 1, 0, C is 0, 1, 0, 0, and D is 1, 0, 0, 0. So everywhere where I had an A in my state table, I'm going to have a 0, 0, 0, 1. So that was here. And here, I believe. And everywhere where I had a B, I'll have 0, 0, 1, 0. And C is 0, 1, 0, 0. And D was 1, 0, 0, 0. And your output is going to be unchanged from the one before. Okay, questions on that? Yes.
Just in case, how did you get the numbers for ABC?
Okay, so there's 2 answers. One of them is I get to decide whatever I want and can't be wrong, except you can be wrong because he said here to use one hot encoding. So I did that just because he's done that before on a test. In general, the only thing that's required is that they be different from each other. So generally what I do is I take my number of states, let's say I have 6 states, and I figure out my power of 2, that's the one that's smaller than, so 2 to the third is 8, 2 squared is 4, so that means I have to have at least 3 flip-flops. So I know I need 3 bits. And so my 6 states, I would say I would do them 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, and 1, 0, 1 would be my 6 states.
So basically, you could just like make them equal to what the number would be.
That's what I do. And that makes it easy, and that makes it easy to grade. But you don't have to do that. You could say, yeah, well, I just, want to make mine different from everybody else, and I'm going to make this one 1, 1, 1. Now, when you do your state assigned table, you have to account for all of them, and so you have to account for all of your values. So when you do your state assigned table, you have to have, we don't have to here because of the one-hot encoding, we don't have to put all 16 values because it's specifically one-hot encoding. But if we did, like if with this one, when we do our table, we would have to include 1, 1, 0, and 1, 1, 1, and make everything over here don't cares. So you have to account for every possibility. Theoretically, we would here, but I'm just not going to.
So, yeah. We had 4 states.
The way I would do this using, if the directions were, use a minimum number of flip-flops. If those were the directions, then I would have A as 0, 0, B as 0, 1, C as 1, 0, and D as 1, 1.
It's 2 to the 2 is the number of states.
Yes.
So, exponential part.
Yes, is the number of states. It also equals the number of flip-flops if you're going to draw the circuit, which is going to be the next thing I do after I real quick show you the difference between this if it was Mealy or Moore. So 0, 1, 0. So if this is what we're trying to detect, we have our reset, which would be same as having a 1, and then we would have 0 is our first one that gets us anything. So 0. This is doing the same thing but mealy. And then, so this would be, so we have, this would be we have a 1. This would be we have a 0. Then if we have a 0 and then we get a 1, if we have a 0 and we get a 0, we stay here. If we have a 0, 1, and we get a 0, then we go here. And I have a 0, 1, and I get a 1, I go here. Okay, so let's look at what happened. And then I'm not done with drawing the diagram. But, so we had if we have just a 1, that's nothing. That can be our reset. But from the reset, if we get a 0, we've gotten to the first stage. Now, we haven't gotten our sequence of 0, 1, 0 yet, so our output is 0. This time we draw our output on the arrow. because the output happens on the same clock cycle. If I have a 1 and I get a 1, then my output is 0 and I stay on the 1. If I have a 0 and I get a 0, I'm still in the same state, but I haven't gotten my sequence yet. If I have a 0 and I get a 1, then I've got a 0, 1, so I'm on my way, but I'm still not there yet, so my output is 0. If I have a 0, 1 and I get a 0, then I've got my sequence. Yay, so my output is 1. The state that I'm in, though, is the state 0, 1, because I don't have a separate state for having found the sequence. I just go back to the state that was 0, 1, which was that state, but my output is 1. If I have a 0, 1 and I get a 1, I'm back to having nothing, and so that would be my state diagram. So you don't put the output on the states that in the Mealy diagram. How many states do we have? What's the minimum number of flip-flops? 2. All right, so I'm going to stop here, and I know some of you probably have to go, and if you have to go, that's fine. If you want to stay, I'm going to do the next problem, which is a Mealy machine, and also you have to draw the circuit. It's a long one.